Okay, so we are moving on to chapter 3. There will be a little bit of information from chapter 2 that will probably be on your test. And it's just things that we needed to know about before we can move on in our content. So, yeah. So now we're going to look at chapter 3. And it is all, well, the first lesson anyways, is all review of what we did freshman year, talking about the development of the periodic table. So we might go through this pretty rapidly. So, essential questions for lesson 1, which are listed on page 84 in your book. What are the steps in the historic development of the periodic table? And how is the periodic table used to predict similarities in similar elements? A review of some vocabulary plus our new vocabulary. The electron cloud is the space that is around the nucleus of an atom where the electrons are found. Some new terms for this lesson include periodicity and periodic law. And the big idea that we are exploring in this lesson is that the periodic table evolved over time as scientists discovered more useful ways to compare and organize the elements. So, let's see. Early scientists needed a system that would show similarities and differences between the individual atoms and as well as the groups of elements. J.W. Dobereiner classified some elements that had similar chemical properties into triads, organizing them according to their atomic mass. And so table 1, which is on page 85 in your book, and it'll come up on the next slide, and then table 2 on page 86 shows 2 of those triads. And from that, it revealed an orderly arrangement of their chemical and physical properties. And this concept suggested that the properties of elements are related to the atomic mass. So this was just early ideas about the periodic table, later disproven. Not saying that there's not similarities between them, but the way he arranged it is not necessarily the way that it is arranged now. Similarities between it, but not exactly the same. So here is the halogen triad, which includes chlorine, bromine, and iodine, and a metal triad that has calcium, strontium, and barium. So looking at the periodic table, we can see that chlorine, bromine, and iodine are in the same group with each other. Strontium, calcium, strontium, and barium are also in a separate but same group, the 3 of them. So there are similarities between them. So they were looking at physical and chemical properties that they have. But he thought they were more related to the atomic mass than anything, which we now know is not true, that it is related to the electron structure. And that's how we organize our periodic table now. So some more research by Dmitry Mendeleev. He put the chemical and physical properties of these elements in a repeated orderly way, and he put them in order by increasing atomic mass. So he was kind of building off what Dobereiner did. He included information like density, melting point, boiling point, and that it all increases as the atomic mass increases. So he was seeing that pattern. He was also able to use some of that information in order to identify new elements and predict what their properties would be. Germanium was one of them that he did. Doesn't talk about it in here that I can see. But he was able to predict that element and what the properties could possibly be based on the elements that were surrounding it when he put these elements into a organized table. So he listed elements in vertical columns starting with the lightest mass, and put elements with similar properties into adjacent columns, and was able to predict some of the undiscovered elements that have since then been discovered. So on page 88, we have this table that is in there. As he said, they were put into vertical columns. Anything adjacent to it, he said that had similar properties to them. He also has like what their chemical formula would be to form an oxide. So all of these, it would be like H2O, Li2O, Na2O, K2O, Cu2O. Here it would just be RO, so just the element with the oxygen. We have R2O3, RO2, R2O5, RO3, R2O7, and RO4. So different ways that they would combine with oxygen to make an oxide. So we had some information about that. The improved version of the periodic table has it arranged in horizontal rows in which elements have similar properties to each other. And the difference in the properties were arranged into different columns. Mendeleev was able to predict properties of elements that had not yet been discovered using the idea of periodicity, which is the tendency to recur at regular intervals. And we see periodicity every single day in our lives. With what? Where do we see periodicity at? So like the periods, right? Yeah. Like they're literally named periods, different periods of the day. You have 8 periods of the day. That's periodicity. Every single day, it is the same thing, right? 8:15 starts your first period class, and that goes to 9:05. Bell rings, you go to your next class. Okay? It's the recurring at regular intervals. What are some other examples of periodicity?
Microwave? Not necessarily. Like a work schedule.
Work schedule as well. Okay, that would be one. Yes, for sure. What else?
Birthdays.
Birthdays.
Any type of holidays.
Mm-hmm. The calendar year in general, right?
Yes.
365 days a year.
Even though it changes every year what day it is.
Not every year. Only every 4
years.
years. But you go through, and first month of the year is always January, followed by February, March, April, May, all the way up to December, and then the year starts over, right? And then each month has a certain amount of days in it. Okay, those are all examples of periodicity. So an example that they give in the book is Halley's Comet appears every 76 years. Mendeleev had many blank spots in his periodic table, just because when he looked at the properties of it and how they combined with different elements, he could tell that there should have been an element there, even though he didn't know what it was. So he predicted those properties. Two of them being Eka aluminum and Eka silicon that he called them. And in 1875, it was discovered, the Eka aluminum was discovered and named gallium. And ecosilicon was discovered in 1886, and it was named germanium. And then he placed elements in groups that had similar properties to each other. So he did not necessarily discover the gallium or germanium. He simply predicted that they would exist. But other people had discovered them. This table, which is on page 89 in your book, just shows the properties of germanium. So where it says predicted, that is what Mendeleev had predicted the properties to be. And if we compare them to the actual properties of them after it had been discovered, you can see that they are really similar, right? Like the atomic mass, he predicted it to be around 72 atomic units, and it is actually 72.61. Without ever even knowing that what it was, he could make a prediction, and he was pretty close. He predicted it would be dark gray. It was more of a gray-white, so it was still gray, just a little bit off on the color of it. Density 5.5, when in actuality it was 5.32 grams per milliliter. Said it would have a very high melting point. Didn't give it a specific temperature, but 937 degrees Celsius is a very high temperature. The formula for oxide, he predicted it to be correct, that it would, one element of ecosilicon would combine with two atoms of oxygen, and so germanium oxide is one germanium atom and two oxygen atoms. He said he thought that it would be slightly dissolved by hydrochloric acid. However, it is not able to be dissolved by it. And then he also was able to predict what formula it would be when it combined to form a chloride. So without actually knowing of the substance, he was able to make a lot of predictions about it and was very, very close with it. And that wasn't the only one. There were other elements that he predicted as well. So, another guy that contributed to the periodic table, a guy named Henry Moseley. Tellurium was placed with oxygen and sulfur into a group because of the similar properties to each other. The tellurium placement was correctly predicted, even though the atomic mass was not. And so he proposed a rearrangement of the elements according to their atomic number. So if we were to look at our periodic table here, which is on page 90 and 91, you also have a copy of that periodic table on the back covers of your book. You can't see that very well, but if you look at tellurium is element number 52. It has an atomic mass of 127.6. Okay. Antimony, which is the element that comes right before it, has a mass of 121.757, and iodine has a mass of 126.904. Okay. So in the previous periodic table, iodine and tellurium would be flipped around because of the atomic mass, because they put it in order of increasing atomic mass. But when they did that, the elements that iodine were in a column with didn't have similar properties to those, and tellurium did not have similar properties to fluorine, chlorine, bromine, and astatine. So by being able to flip them around by their increasing atomic number, which is the number of protons, it made more sense because tellurium shares some properties with oxygen, sulfur, selenium, polonium, and livermorium. And iodine shares properties with fluorine, chlorine, bromine, and astatine. So they started putting the periodic table in order of increasing atomic number rather than increasing atomic mass, and that is how it is arranged today. So the periodic table that's up on the wall is arranged like that. Periodic table that is in your book is arranged like that. And depending on the periodic table you look at, it can include several different bits of information about it. The one in our book shows if it is a metal, a non-metal, or metalloid. It gives the element name, the atomic number, the symbol for it, the atomic mass. It also tells us if it is a gas, a liquid, or a solid, and if it is synthetic, meaning it is made in a laboratory. Okay. Our periodic table up on the wall there does not show us as much information, right? And then the periodic table that I printed off for you has a little bit more information on it because it also tells you specifically what category of element it is. Like if it's a alkali metal, if it's a transition metal, if it's a halogen, if it's a noble gas. Tells you that information as well. So different periodic tables can tell you different things. For the sake of being in high school chemistry, you guys don't need to know nearly as much stuff on it, so I give you a pretty simple one. Have ones that look like this. These are really old because it doesn't even have like these element names here, which have since been discovered and named. Okay. This periodic table has specific heat, first ionization energy, atomic radius, ionic radius, most stable abundant isotope, discovery year, and the scientist and the country that it was discovered in, the crystal type at absolute zero, common uses, derivation of name, electronegativity, standard reduction potential, longest lived radioactive isotope, half-life of longest lived radioactive isotope, abundance in crustal rocks, and radioactive symbol. And you're going, I have no idea what any of that means, right? It's all right, you don't, where am I at? What? Oh. Anyways, don't worry. I don't use any of that information that I just read off. I teach high school chemistry. I took it in college, several years of chemistry in college, and I didn't use most of that information. So I don't give you this periodic table for that reason. I print off a much simpler one because you don't need all that information. It just takes up space and you don't know what it means and we don't need it. So, but just showing you that different periodic tables, that depending on the source, can have different bits of information on it. Okay. So as of right now, and I don't know of any other elements, but that doesn't mean that they're not trying to make them, but there are 118 elements that have been discovered or synthesized, meaning made in a laboratory. Mendeleev's table only had 60 elements on it. And the atomic number will increase by 1 as you move from element to element. If you read from left to right on the periodic table and then move down a row and continue reading left to right, okay, it will increase by 1. The atomic number increases by 1, which tells us the number of protons that an element has. Number of protons gives the identity of an element. And then we have those transition elements, and inner transition elements were unknown until 1869. So Didn't really know about them. A lot of them are synthetic, but they're a lot more rare than some of the other elements that were on that first periodic table. And then noble gases were unknown until somewhere between 1894 and 1898. And the reason for those being unknown for a period of time is because they're unreactive elements. So their outer energy level, which we'll talk more about this, is completely full of electrons, making them stable elements, meaning they don't want to react with other elements. So if you don't find them in a compound with something else, then it's really hard to find them. I mean, they've been discovered since then, obviously, but. Other patterns that we see with the periodic table, with exception of the first row, which is hydrogen, right? Hydrogen, helium are the only ones in the first row. But everything below that in groups 2 through 7 those rows are going to begin with a metal and end with a noble gas. Hydrogen is over there because it has 1 electron in its outer energy level, even though it is a non-metal. And you can see that pattern a lot better on the periodic table in your book, because hydrogen is the only yellow element over on that side. The rest of those are all blue. The idea that the physical and chemical properties of elements repeat in regular patterns when they are arranged in order of increasing atomic number is known as the periodic law. So using that periodicity of the characteristics, both physical and chemical, of these elements and putting them in a specific order according to their increasing atomic number, that's using periodicity, and we call that periodic law. All right. Any questions about that? No? Okay. That's all I got for notes for you today.